All right, so continuing on with our lesson about random variables. So I know some classes got here yesterday, so if you were one of those, you can just sort of move forward past this a little bit. But so random variables can be two different types. They can be discrete and continuous. And if those words sound familiar, that's because they are. We learned about discrete and continuous data in the beginning of the year. And if you remember, discrete data is whole number countable data versus continuous is data that could be measured as a decimal of some kind. So if you're looking at data, or in this case, we're looking at variables with values that are whole number values, like the number of kids a couple has, let's say, then that would be discrete, versus somebody's mile time would be continuous, because you can have a 10-minute, 30-second mile time, a 10-minute, 30-second, and 5-millisecond mile time, etc. So for discrete random variables, that is what we're going to actually be focusing on for first part of this lesson, and then last we'll look at continuous. So hopefully if you don't have that part filled in, you should be filling that in now. There are two types of discrete random variables, and the first thing we're going to start with is what I call the create your own random variable. So for this, we're going to look at an example, and then we're actually going to calculate the mean of this random variable. And again, if you're not in third period, you haven't done this yet, third period, you may move on. All right, so let's look at an example. Okay, so in our example, this is going to be the first type of discrete random variable, which is what I call create your own. So it says you draw a card from a standard deck. If you get a red card, you win nothing. If you draw a spade, you win $5, and for any club, you win $10 plus an extra $20 for the ace of clubs. Let X equal the amount of money you win. So part A, create a probability model for the amount that you do win. So let's start with that. The reason why I call this create your own is because you quite literally have to usually create your own probability model here. So for part A, so we have a few different things that can happen, and X is the amount of money that you win. And so we're going to start with creating a probability table or probability model for the amount that you win. Okay, so I'm going to put X equals amount of money, but you can just put X probability on the bottom. Okay. All right, and we are going to certainly be using our calculators here. So the amount of money you can win. Well, according to this information, the lowest amount of money you could win is $0, and that's if you draw a red card. It looks like if you draw a spade, that is going to be $5, so you could win $5. If you draw just a regular club, that's going to be $10. And if you draw the ace of clubs, basically you get $10 plus 20 more because you drew the ace, so that's $30. And those are all your possible amounts. Next, we do need to find the probabilities of each of these outcomes. And so in this case, this is your standard deck of cards. Half of the deck is red, and so the probability that you make $0 is 0.5. Half of the deck is red, and if you don't know much about cards, there are 4 suits: hearts, diamonds, spades, and clubs, and each suit has 13 cards out of 52, or in other words, each suit is 1/4 of the deck. So for the spades make up 1/4 of the deck, which means that we have a 25% chance of getting $5. Now here's where the rest of this gets kind of decimally. So we have 13 cards left, which make up the clubs. And according to this, 12 out of 52 of those cards are going to be clubs that are not aces. And so if you divide 12 by 52, that probability, and I am rounding, which is bad, is 0.230769, etc., or 0.23, we'll just round it to 1. And then to find the remaining, you would do 1 divided by 52, or you could add these 3 up and subtract from 1. And so if you do any of those options, you should get about 0.019. Okay, so we have our probability model for X, the amount of money you could win playing this game. So next we get into another idea that comes from random variables, which is oftentimes it's really kind of helpful and useful to find the mean of a random variable. And in fact, part B, even though it doesn't say the mean, is asking for the mean. It says, how much would you expect to win? And the interesting thing about random variables is how much you would expect to have is the mean. And so we're going to write this down here and come back. The mean of a random variable is the same thing as expected value. So mean tells us how much we should expect from this random variable. Again, third period, move on. And the way that it works, the expected value or mean, which by the way is notated like so, our little mean symbol with a capital X, or we could do E of X like this, that's expected value. The mean is calculated from our table. And so if we're looking at a probability table, we have a value on the top with the probability on the bottom, value on top, probability on the bottom, and so on. And so if I want to find the mean or expected value, same thing, the way I do that is I actually take my first value, I multiply by its probability, and then plus the second value times its probability, plus the third times its, and so on and so forth. And so if I have a table, then I would take each of my values and probabilities, multiply them, and then add them together. All together, if you want a fancy formula, it is the sum, hopefully we remember that notation, of each value times its probability. So that is how we calculate the mean. And any term that has anything to do with mean, so average, mean, or any kind of version of the word expected. So how much should you expect? What do we expect? What do you think you're going to get? Any sort of indication of, hey, what are we expecting? Anytime that question is asked, they want you to follow this formula and calculate the mean. So let's go back up and let's do that. So part B, let's go ahead and calculate the mean here. So the expected value of X. And so to do that, and you can go ahead and pause this if you want and just check your work. I am going to take 0 times 0.5 plus 5 times 0.25 plus 10 is my next one times 0.231 plus 30 times 0.019. So I'm going to plug this into my calculator, and then that answer is how much I should expect to win. And so plugging that in, I should get $4.31. Okay. And so that's sort of a weird concept in this case because I'm just pulling one card at a time. But what it tells me is that if I played this game multiple times, I should expect to win approximately $4.31 each time, which, you know, maybe that encourages me to keep playing the game. So that's how to calculate expected value. And lastly, we come to the dreaded standard deviation. It's back, folks. It's back. So along with mean always comes standard deviation. They're never separate for very long. And so now we have to find standard deviation because, as I'm sure you super duper remember, standard deviation is the approximate distance of most values from the mean. And so we are going to find standard deviation of the random variable, and there is sort of a way to do it that's a little different from our crazy formula that we saw before. There's also a way to find standard deviation using a calculator, which you have in your notes and you are certainly more than welcome to use. But frankly, it's pretty rare that you're asked to find standard deviation by hand. And even if you are, you can use the calculator shortcut to do that. So here's how this works. Basically, we're going to find standard deviation, but we're going to start with this thing called variance. And variance doesn't really have a pretty real-life application, but it's super duper important for random variables. And so what you need to remember about variance is standard deviation squared, which I think we mentioned like when we found standard deviation. So variance is standard deviation squared. The way we calculate standard deviation from a random variable goes like this. Again, I'm sort of starting with the table. And so for each value on the table, so we'll start with value 1, I'm going to take my value and I'm going to subtract the expected value, the mean, from it. Once I'm done doing that, I am going to square whatever this difference is. And finally, I'm going to multiply that squared difference by the probability from the first guy. Then I'm going to do the whole shebang again. So x2 minus the mean squared times probability 2, and so on and so forth. So once I do all of this, that is actually going to get me the variance, or we abbreviate it var of x. Once I get my answer for the variance, to get standard deviation, I will simply square root my answer. And yes, this is a tedious formula. It has come up actually on an AP test back in the day, but it was a problem like this where our table was relatively short and sweet. And so our formula for standard deviation is the square root of the variance, which is, I think in your book it's written this way actually, P1 times X1 minus, oopsie, mean of X, my bad, squared plus P2 times X2 minus mean squared, etc. Square root over everything. Okay. So that's gross, but whatever, it's doable. Let's just do it. So let's go back up to our example. We found the mean. So now let's go ahead and actually calculate the standard deviation. So part C. Okay, I know the expected value, which is the same thing as mean, is 4.31. So we're going to start with our first guy, which is gross, but let's do it. So let's start with the variance. My first difference is going to be, so I know I'm multiplying by my first probability, which is 0.5. 0 minus 4.31 squared, plus my next one. So 0.25 times 5 minus 4.31, and then squared, etc. So I'm going to write all of that. And then once you have that answer, so once you plug in that whole shebang to your calculator, that will get you the variance. And once you're done with that, you are going to square root your answer to get the standard deviation. All right, so sorry I trailed off on the other side there, but after you plug all this into your calculator, unless my calculations are incorrect, which they could be, ooh, they are, pause. Okay, that's better, sorry. So you should get, there we go, 29.4255 approximately for the variance. So this should get you the variance of x. Which is nice, but usually that's not what we're asked for. And in fact, in this example, we are not asked for the variance, we're asked for standard deviation. And so to get standard deviation, we are simply going to square root our answer. So our standard deviation will be the square root of this number, which is approximately 5.42453. I guess not approximately, but there it is. So there's the standard deviation. Again, there's a formula for this, but there's also a shortcut on your calculator. Either way, it's pretty rare that we really care about standard deviation from what I like to call create your own discrete random variable. All right, so this is pretty much what you need for discrete random variables. We are now going to go on to continuous random variables, and actually the punchline for that is we've kind of already dealt with them before. And so moving on past your discrete random variables, we know that continuous random variables can be any values that take decimals. And so there are really two main types of discrete random variables. One of them we've used a ton, and that's a normally distributed random variable. The other one is a uniform random variable. And we are going to briefly talk about a uniform random variable and then do an example with a normal random variable because you've done normal stuff before. Now, I know you might not remember, but it shouldn't be too bad. So uniform random variables, remember, uniform distributions look like this. So if I have an x-axis, uniform distributions essentially are uniform normal curve, or uniform density curves, there we go, essentially look flat. So if a distribution is is uniformly distributed, it is flat. It looks like a box. And so the way this works is, so let's say that I was looking at the distribution of, well, actually, let's say, it's a discrete random variable. So let's say I was looking at the distribution of commute times to a certain city. And let's say that the distribution was uniform and it spread between 15 minutes and 37 minutes. Okay. And it could be any time in between, to the millisecond, to the nanosecond, to anything. So let's say that was our distribution. A uniform distribution would essentially start at 15 minutes, go to 37 minutes, and look like a box. The other piece of a uniform distribution is very much like a normal curve. The area underneath the box, or the curve or the line, must add up to 1. And so I'm sure you super duper remember your geometry. Actually, for our purposes, let's change this to 35, make this nicer. So for the purposes of our geometry, hopefully you remember this, the base of this little rectangular uniform distribution starts at 15 and goes to 35, which means the length of this rectangle is 20. And if the area has to equal 1 underneath, then essentially you're doing the length times width, which we don't know, has to equal 1, which means the height, if you want to think of it that way, which means the height has to be 1/20th. So that means this height is 1/20th. I know you're thinking, what on earth are we doing right now? You actually have a couple homework questions that ask you about this, and my AP kind of is into it this year, so here we are. So this is an example of a uniform distribution. And so basically what you might be asked is if they say, hey, let's let y be the commute time of a randomly selected, I don't know, car, they might want to know, hey, what is the probability that y is, I don't know, less than 30, less than or equal to 30. And so for that, what you would do is you would say, okay, 15 to 35, 30 is about like here. So 15 to 35, I would actually be interested in the commute time being between 15 minutes, since that is the minimum, and 30. So I would be interested in the area in this section of the rectangle. And so to find that probability, I would say, okay, well, what is the length of this part of the probability, or of this part of the curve, which the length of this part would be from 15 to 30 minutes, so that would be 30 minus 15, which is 15. And then we would multiply it by the height, which is 1/20th. So times 1/20th. And that probability would be whatever decimal you got, or in this case, we can just leave it as a fraction or a decimal because 15 out of 20 is 3/4. Okay, so that's how a uniform distribution works, and I am sorry for the jumbled explanation there. My dog is trying to get into this room as we speak. Anyway, so that is a uniform distribution. You do have a question about it on your homework, and this is the type of thing they would want you to do. But this is actually the least common type of continuous random variable. The most common type of continuous random variable is a normal random variable, and for that, we are going to consider an example. So a normal random variable is basically just a variable that is normally distributed. And so, for example, we typically look at things that are some kind of measurement. And so the example I have is, that's what I thought it was. So is veterinary expenses for a dog. I know, this really gets you right at home. So let's say we are interested in X, which is the amount of veterinary expenses spent on a randomly selected dog. Spent on a randomly selected dog. And let's say that we know, because the problem tells us, because at this point they have to, that the mean or the average amount that one spends on veterinary expenses for dogs is $100 with a standard deviation of 30. Let's say, so $100 with a standard deviation of 30. They can ask you all sorts of probability questions. And again, this is all pretty similar to what we did before, but we didn't tend to use the word probability. And so what they might ask you, for example, is, all right, well, what's the probability that your veterinary expenses are between like $95 and $130, let's say. So they might ask you, hey, what is the probability that the amount you spend falls between or falls in this range? And to answer that, remember, you're going to use your calculator. We're not trying to do this with the empirical rule at this point in the year. But if you want to look at a probability distribution or a picture, the way you're going to do that is by looking at the normal curve. And remember, from back in the day, we typically label the normal curve with the mean in the center, and we label 3 standard deviations out in either direction. And so if I did that, I would have the following distribution. And this would be the amount spent on dog. Okay. So in this case, if I'm interested in the probability that your vet bill is between 95 and 130, then I am interested essentially in the area from about here to 130. And then remember, from back in the day, the way we're going to find that probability is by plugging in your calculator and using normal CDF. And so I'd put normal CDF. And remember, you have options. You can draw the curve I just drew and then just put the decimal answer. That is totally acceptable. If you are showing calculator work, that's fine as well, but you need to label what you are showing. And so remember, if I want the amount between 95 and 130, 95 will be my lower bound, 130 will be my upper bound, my mean is 100, and my standard deviation is 30. And remember, we need to actually label that. And so we would do that. And then from here, we are going to plug into the calculator, which I'm sure you all super duper remember how to do that. But just in case you don't, you are going to go to second vars. And you are going to scroll down to number 2, which is normal, or I think it's number 2, normal CDF, and then you should just plug these in as is. When you plug these in, you should get 0.4075, so 0.408, or about a 40.8% chance. All right, folks. So remember, the main takeaway here actually is for continuous random variables, you do occasionally have a uniformly distributed random variable, but almost always for continuous random variables, we are almost exclusively looking at normal random variables.